Each member of the RAN, regardless of his or her rank, is a trained firefighter who, at a moment's notice, may be called upon to fulfil that role. Imagine yourself in this situation. You're operating the nozzle as you make a door entry into a burning compartment. As you enter, there's a thick, hot layer of smoke hanging a metre above the deck. The heat from above is so intense, it's soaking through your PPE, but you keep pushing deeper into the compartment. At first, you can't see any flames, but then suddenly, the whole top of the compartment is ablaze. You're forced to the deck. Instinctively, you blast the fire with your hose, but the heat and steam are so severe that you and your team are forced to withdraw. In the meantime, the fire continues to grow. With a different approach, this fire could have been extinguished, and the safety of the firefighters needn't have been compromised. In recent years, firefighting techniques have improved significantly, and so the RAN has revised its firefighting policies and procedures. This now brings the Navy into line with the latest methods employed by civilian and military firefighters worldwide. The purpose of this DVD is to demonstrate new and improved hose techniques, which not only make firefighting safer, but also more effective. In Part 1, we're going to examine rapid fire progress and hose techniques. In Part 2, we'll take a look at both direct and indirect methods of hose attack. And in Part 3, we'll follow a worst-case training scenario through an entire evolution. But first, a simple experiment to demonstrate the volatility of smoke. In this flask are wood shavings, which I'm heating over a gas flame. When the temperature of the wood reaches 150 degrees Celsius, the cellulose decomposes and begins to release flammable vapours. This process is known as pyrolysis. Although the shavings themselves are not burning, the pyrolytic gases are a rich source of fuel, which, when ignited, combust readily. In a major fire, the same principles apply, but on a considerably larger scale. Radiant heat causes flammable materials to pyrolyse, and these gases, along with the unburnt products of combustion that we know as smoke, combine to form a highly volatile fuel. Rapid fire development within a compartment can be broken down into 5 distinct stages. Ignition, the growth stage, flashover, a fully developed fire, and decay. Ignition occurs when a flammable material reaches its flash point and commences burning. The growth phase is when a fire becomes self-sustaining. To begin with, the flames are localised, but as the fire continues to grow, hot fire gases are produced. As we know, heat rises, and as the hot gases reach the top of the compartment, they spread laterally, carrying heat away from the source of the fire. The hotter the gases, the more they expand, and with nowhere else to go, the smoke layer is forced down. As the heat continues to build, the hottest gases near the top of the compartment reach their ignition temperature and begin to burn. This is sometimes known as rollover. Flashover is the transition from the growth stage into a fully developed fire. The heat from the seat of the fire, along with the burning of overhead gases, radiates throughout the compartment, raising the temperature of the surrounding materials. All exposed flammable surfaces within the compartment begin to pyrolyse. When these hot fire gases reach a critical temperature somewhere between 600 and 800 degrees Celsius, auto-ignition occurs. The whole compartment explodes in flames and the temperature is instantly raised to above 1000 degrees Celsius. The transition to a fully developed fire is complete when all combustible materials within the compartment have reached their ignition temperature and are burning freely. The intensity of the fire is then determined by the availability of fuel and oxygen. And finally, the decay stage is reached once the majority of the fuel within a compartment has been consumed. Rapid fire progress refers to a number of phenomena which can lead to extreme fire behaviour. These events are so powerful that PPE and breathing apparatus provide very little protection. Personnel exposed to such ferocity would have little chance of survival. They are flashover, backdraft and fire gas ignition. As we've already seen, flashover is the rapid transition to a fully developed fire, once fire gases have reached their auto-ignition temperature. A backdraft is a massive release of energy triggered by supplying oxygen to an underventilated fire. In this demonstration, we're going to use this wooden box to replicate the behaviour of an oxygen-starved compartment fire. With the door open, the fire has a good supply of oxygen and it's already starting to get pretty hot. That wispy white smoke is the wood starting to pyrolyse. The flames you can see at the top of the compartment are the hot fire gases igniting. And after just a couple of minutes, we have flashover. It's now a fully developed fire. When we seal off the opening, the fire quickly consumes the available oxygen and the flames die back. But the space is still full of hot fire gases, unburned fuel, just waiting for oxygen and an ignition source. When we open the door, oxygen is reintroduced and the hot gases mix with the air, creating a highly combustible mixture. All it takes is one hot ember to ignite this mixture and the burning gases burst into life. They expand rapidly, but because of the confines of the compartment, the pressure builds up and the burning gases explode through the opening with tremendous force. That's a pretty powerful backdraft considering the small amount of smoke involved. Imagine what would happen to a hose team making a door entry into a large compartment under similar conditions. The consequences of an explosion on that scale would be devastating. Potentially just as destructive as fire gas ignition. In a compartment fire, we've seen how the pressure of the expanding gases can push the smoke layer lower, but these gases can also be forced into surrounding compartments through vent ducts, cable trays or voids. If any of these compartments contains an ignition source, these volatile gases can explode. The behaviour of every fire is highly unpredictable, but there are a number of warning signs which indicate the onset of rapid fire progress. Being able to interpret this behaviour and acting accordingly is crucial to the safety of firefighting teams. The signs of an impending flashover are painful overhead heat forcing firefighters down to the deck, a low smoke layer, flames running through the overhead gases, high rates of pyrolysis, and a sudden increase of turbulence in the smoke layer. As we've seen, a backdraft results from an underventilated fire being given a supply of oxygen. The classic signs of an impending backdraft are the lack of a visible flame or a blue flame, dirty brown, yellow or white smoke pulsating through small openings, an extremely low smoke layer, intense heat within the compartment, and a whistling noise from air being drawn into the compartment when a door is opened. The warning signs of rapid fire progress all have one thing in common: the presence of hot fire gases. By aggressively cooling these gases, firefighters can take control of the fire environment and prevent flashover, backdraft and smoke explosions. We'll now take a look at the hose techniques used to control and extinguish this type of fire. They are short pulse, long pulse, penciling and painting. The short pulse technique is used for gas cooling in the immediate area. This dilutes and cools the flammable gases within the smoke layer and prevents them from reaching their auto-ignition temperature. Adjust the setting of the nozzle to produce a medium-wide spray pattern. This produces the optimal droplet size of around 0.3 of a millimetre, which hangs in the air for about 3 to 4 seconds. The small size of the droplets has the effect of vaporising within the gas layer, providing a cooling effect whilst limiting steam production. To gas cool, operate the nozzle in very short pulses. Fully open and close the bail handle in one quick movement. To be effective, the nozzle must be aimed directly above the firefighter's head and constantly move from one area to another. Long pulses, as the name suggests, are 2 to 3 second bursts, also used for gas cooling. The nozzle is adjusted to a narrower setting of about 60 degrees. Long pulses are aimed at a lower angle into the hot gases that have flames running through them. This allows the firefighters to cool large areas and penetrate deeper into the compartment towards the seat of the fire. The correct technique for the long pulse is to open the bail handle quickly and close it smoothly. In practice, gas cooling is a combination of long and short pulses. When you get to the stage where water spray can be seen falling out of the gas layer, you'll know it's having the desired cooling effect. Painting and penciling are techniques for directly attacking burning materials. Unlike the hard-hitting jet style of attack, these techniques use less water and produce very little steam. For penciling, set the nozzle to a narrow stream and pulse the bail handle quickly, lobbing fat droplets of water directly onto the seat of the flame. For painting, open the bail handle quickly and gently sweep the water in an arc across the burning material. The one thing all these methods have in common is their economic use of water. In shipboard firefighting, flooding and the creation of free surface water can compromise a ship's stability. The use of these techniques in the appropriate situations helps alleviate this problem.